Now let's prove a basic result about Carmichael numbers. So I'm going to assume that you all know what a Carmichael number is. And let's begin. So what this theorem says is there is not a Carmichael number of the form PQ, where P and Q are distinct odd primes. We're going to prove this by contradiction. Assume, for the sake of contradiction, PQ is a Carmichael number. And without loss of generality, assume P is greater than Q. And now we know P and Q are distinct from a previous result called Courcelle's criterion, and we're going to need the other piece of that, so I'm going to write it down. So Courcelle's criterion says if A is a Carmichael number, actually A is a Carmichael number if and only if P minus 1 divides A minus 1 and P squared does not divide A for all primes dividing A. And so this is why we know that P and Q are distinct, because no square ever divides a Carmichael number. Okay. Now we're going to use this piece. So PQ is a Carmichael number, therefore P minus 1 divides PQ minus 1 by the first part of Courcelle's criterion. Now notice that P minus 1 times Q is simply equal to PQ minus Q. That's just a separate statement from above here, but it's just a true equality that we can write down. And this one says there is some integer k such that P minus 1 times k is equal to PQ minus 1. Now we're going to subtract these two equations. And when you do that, you get P minus 1 times Q minus k equals minus Q plus 1. And so I didn't do that the smartest way. We should have subtracted the other one away, but we can flip the signs, multiply both sides by negative 1, and we get this is equal to Q minus 1. And this says P minus 1 divides Q minus 1. This is impossible because P is bigger than Q. And so we have a contradiction. And therefore there are no Carmichael numbers of the form PQ, or P and Q are distinct primes. So basically what this tells us is if we have a Carmichael number, it's a product of at least 3 distinct prime numbers.